Welcome back. In the previous lecture, we discussed Bose-Einstein statistics. And prior to that, we have been discussing Maxwell-Boltzmann statistics. In Bose-Einstein statistics, we started further subdividing the cell into various compartments. And then what we did was we derived an equation. The final equation was resembling almost similar to the Maxwell-Boltzmann statistics. The major difference between the two statistics was highlighted over there. And further, we also discussed that we will not put any restriction in the number of particles, number of phase points occupying a particular compartment of the cell. In other words, the Pauli exclusion principle was not adhered to. But when we are dealing with the electrons, then we know that you cannot put more than 2 electrons in a one particular orbital or suborbital. Pauli exclusion principle has to be followed. So in the way we described in Bose-Einstein statistics, here also let us begin by considering ni number of phase points in the ith cell. So as usual, we fix the number of phase points in the ith cell. These phase points can be electrons, it can be molecule, it can be etc., anything else. However, when you are specifically considering the electron gas, then see the comment. Now consider electron gas where Pauli exclusion principle applies, which was not considered in Maxwell-Boltzmann or Bose-Einstein statistics. Right? So what it is saying? That now you don't want more than 2 electrons or 2 phase points in each compartment, right? So that means now there can be no more than 2 phase points in each compartment, and this is the same principle that applies to arrangement of electrons in atoms. What it means, in other words, is that no 2 electrons in the same atom can have same set of quantum numbers. If all the other quantum numbers are same, at least spin will be different. This is the Pauli exclusion principle. That means maximum 2 electrons with oppositely directed spins means maximum number of representative points in a cell is therefore twice the number of compartments. You can have a compartment in that you can put maximum 2 phase points. So that means if you know the total number of compartments, then the number of representative points in the cell is therefore twice the number of compartments, because each compartment can accommodate 2. But now for the representation purpose, let us use the compartment term for half-filled compartments. Don't misunderstand. When I say 2 phase points can be put in a compartment, I will further divide that 2 into 1, 1. That means half-filled compartment. So in each compartment, I will put only 1 phase point. Therefore, now you consider just 2 cells, I and J. As usual, we have been considering I and J. And each divided into 4 compartments. Now, the way I will represent it is, you consider let us say I say cell I. and then cell J, again I will put 4 subcompartments or 4 compartments. Now this each compartment means we can only fill one phase point. Remember what we just discussed, that let us use the term compartment for half filled compartments. So half filled means I can put only one in each compartment. So let us say I put 1, 2, 3, then you can have the next one. You start from here 1, 2, 3. You can have another one 1, 2, 3, and there can be another arrangement 1, 2, 3. There are 4 possibilities, 4 different ways of arranging these phase points in cell 1. And in cell J, I only want to put only one phase point. So this can be here, this can be here, or this can be here, or this can be here. So this is your cell J. So what I have, 1, 2, 3, 4, Wi is equal to 4. 1, 2, 3, 4, Wj is equal to 4. So therefore the total number of arrangements is obviously Wi times Wj, which is equal to 16. There are 16 possible arrangements. With this, Ni equal to 3 and Nj equal to 1 with the adherence of Pauli exclusion principle. That means in general, I can write this weight is equal to product of Wi. So it depends upon the number of cells. You have I, J, K, L, etc. If you know the weight of each corresponding to each set of cells, then you multiply all those, you get the overall thermodynamic probability. We have talked about 4 compartments in a cell. Let us now talk about G compartments in the cell. Let's say we focus on G compartments in the cell. Ni are occupied. Suppose if there are only Ni number of phase points, if there are total G compartments in the cell and each compartment can have one phase point, that means if Ni are occupied, G minus Ni are empty, because there are total G compartments. So we have occupied and we have empty. That means there are 2 kind of groups. There are 2 groups: occupied compartments, empty compartments. That means we are talking now occupied compartments and unoccupied compartments. I hope you realize that how this discussion is proceeding now to slightly different direction. Earlier when we were talking about the Bose-Einstein statistics, this kind of restriction was not there. There we could put any number of points in any compartment, but here there is a restriction that if each compartment can only accommodate only half filled compartment, which we are representing as only one phase point can be put in each compartment. So with this treatment, now we get down to occupied compartments and unoccupied compartments depending upon the total number of phase points. All right. How many compartments are now occupied? One compartment can have only one phase point, and if there are Ni phase points, then Ni compartments are occupied, and remaining G minus Ni, these compartments are unoccupied. There are total of G compartments. So once we know how many are total, how many are empty, how many are occupied, then we can assign a thermodynamic probability to this kind of arrangement. That is, number of ways of dividing compartments into occupied and unoccupied. Total, that is G factorial divided by N factorial divided by G minus Ni factorial. This is for I cell of type I. Similarly, there can be J, there can be K, there can be L, etc., etc. Therefore, the general expression for the thermodynamic probability of a given macro state in Fermi-Dirac statistics is you need to take product of all these quantities. You have Wi, you multiply by Wj, Wk, Wl, that means overall product of G factorial divided by Ni factorial into G minus Ni factorial. This is the general expression for thermodynamic probability. Now you know that once we have an expression for thermodynamic probability, from that we can now move towards other derivations. For example, you know S is equal to K log W. W can be connected with entropy. We also discussed that W sometimes is not very easy to take forward for derivation of other equations, rather it is log W. So instead of W, if you work on log W, you will see that the derivation of rest of the equations becomes easy. So once we have W, which is product of G factorial over Ni factorial into G minus Ni factorial, as usual take the logarithm of this. When you take the logarithm of this, this is product becomes a summation log Gi minus log Ni factorial minus log G minus Ni factorial from this. Now usually the total number of compartments and the total number of phase points is very large. In that case, we can use Stirling approximation. Let us use Stirling approximation. So log G factorial is G log G minus G. Log Ni factorial is Ni log Ni minus Ni. Similarly, log G minus Ni is equal to G minus Ni log G minus Ni minus G minus Ni. So anyway, when you expand all this, eventual resulting equation is log W is equal to summation G log G minus Ni log Ni minus G log G minus Ni plus Ni log G minus Ni. You can easily derive this equation from the upper equation by using Stirling approximation. Please do try that. Okay, so now we have an equation which is in terms of log W. Once we have log W, now we can take it forward. How? Same usual procedure. We need the state of maximum thermodynamic probability. For a maxima, as we have already discussed, you need to take the derivative, it should turn out to be 0. So therefore, for a state of maximum thermodynamic probability, your d log W, it can be represented as log G minus Ni naught. Actually, you need to take derivative of this, you should end up with this equation. And Ni naught is the number of phase points in ith cell in thermodynamic equilibrium. The derivation is similar to that we discussed in Bose-Einstein statistics. And as we have been always discussing, that you cannot treat this logarithmic function and dni function separately. You cannot say either this is equal to 0 or this is equal to 0. And if you cannot say, then we need to come up with a method in which you can treat these two independently and then come up with some equation. In order to achieve that, what we have been doing is to put some constraints. And those constraints are the total number of phase points has to be constant. That means when you add up all the changes, that should turn out to be 0. Right? This is something which we have done earlier, that is summation Ni is equal to n and summation Ni Ei is equal to E. right? So by using these two expressions, you can arrive at dni summation equal to 0. You can also arrive at summation ei dni equal to 0. And then, as done earlier, you use method of undetermined multipliers, log b term and beta term with the appropriate sign. Then add to this equation. When you do that, then you have these two parts. One is this bracketed part, other is dni part outside. Now you can treat these independent and find out for what expression of b and beta these can be treated as independent. That means you set this equal to 0. I have log g minus ni naught by ni naught is equal to log b plus beta ei if you set this entire thing equal to 0. Now we are moving closer towards our result. From the previous equation, we got log g minus ni naught over ni naught is equal to log b plus beta ei. Once you remove the logs, the expression that you get is ni naught upon g equal to 1 plus beta exponential beta ei plus 1. Here also, you remember in Bose-Einstein statistic there was a negative sign, and here we are getting a positive sign. This one is Fermi-Dirac distribution function for the state of maximum thermodynamic probability. So by now what we have three different expressions which can talk about population of various states. One is in terms of Maxwell-Boltzmann distribution. Second one was in terms of Bose-Einstein statistics. And the third one which we talk here is Fermi-Dirac distribution function. When you compare one with the other, you will see that in Maxwell-Boltzmann distribution you were not considering further compartmentalization of the energy levels. Whereas when we started discussing the Bose-Einstein statistics, that distinction was made, but we said that let us not apply any further restrictions. Further restriction means no rules like Pauli exclusion principle etc. should not be applied. We came up with some final equation, and then we thought that let us now extend the developed theory for the systems in which the Pauli exclusion principle is applicable. One such system is electron gas, and with that type of arrangement we have this equation which is the Fermi-Dirac distribution function for the state of maximum thermodynamic probability. So by now we have discussed three different distribution functions, but in details we took forward the Maxwell-Boltzmann distribution. By using any one of these distribution functions, you should be able to establish connection between the number of molecules in a particular set of energy levels, molecular partition function and canonical partition function. In statistical thermodynamics, when you are focusing on population or you are focusing on any thermodynamic quantities, it directly connects you with various energy levels, and it also connects you with the temperature, it also connects you with degeneracy if there is any. The distribution function under certain circumstances may resemble, but you will appreciate that the overall discussion on statistical thermodynamics, whether you talk in terms of Maxwell-Boltzmann distribution or you talk about other distribution function, the eventual goal is to get thermodynamic quantities in terms of molecular partition function. Why specifically I am not saying in terms of canonical partition function? you can have canonical partition function, you can have discussion in terms of micro-canonical ensemble, you can have discussion in terms of grand canonical ensemble, but we said that we will restrict to N, V and T because these are the common conditions which are applied. Under constant volume, heat supplied is equal to change in energy, internal energy. At constant volume, derivative of internal energy with respect to temperature is heat capacity. So therefore, by applying those restrictions of constant volume NVT, we took the discussion forward. But in most of the equations that we derived here, or the equations which we discussed taking forward to equilibrium constant, were for ideal systems. We have not gone too much into details of non-ideal system, because when you consider non-ideal system, you have to start considering interaction potential energy, which is zero if the system is not interacting. Therefore, the discussion on non-ideal system or non-ideal gases thus was done based upon the virial coefficients, where we talked about second virial coefficient, third virial coefficient, etc., etc. We did not go too much into details from the virial coefficients, although we connected the virial coefficient with canonical partition function, or we connected the virial coefficients with the other parameters which were routinely discussed in statistical thermodynamics. While dealing with the various systems, we have to be careful about not overcounting the number of states. When I said not overcounting the number of states, that means the arrangements which appear again and again. And therefore, we applied the factor which is called the degeneracy factor. Especially, this was more evident when we were talking for the vibrational contribution to partition function. Therefore, overall, now with the discussion on statistical thermodynamics in terms of all three distribution functions, we should be able to connect any thermodynamic quantity with the molecular partition function. As discussed, if you want to go beyond the ideal systems, then we need to bring in more parameters. We need to talk about virial coefficients. Many problems can be set and solved based upon the Bose-Einstein distribution function or Fermi-Dirac distribution function. Please do those. And their connection with thermodynamic properties, with thermodynamic functions should be made. We will conclude today's lecture by realizing that the various thermodynamic quantities, when I say, I mean Gibbs free energy, Helmholtz free energy, pressure, enthalpy, entropy, internal energy, can not only be determined by using calorimetry or direct calorimetry, but they can be determined by the knowledge of energy levels, by the knowledge of degeneracies, in other words, by the knowledge of spectroscopic principles. I hope the discussion was useful, and I also hope that, as I have repeatedly said, that you will be able to connect the molecular partition function or canonical partition function with various thermodynamic quantities and evaluate them. Thank you very much.